Good evening. I'm all right. Yes. Welcome to our third lecture in this year's spring astrophysics series. You can hear me in the back? Is that what you're raising your hand? Yeah, okay. Excellent. It's a privilege to introduce another familiar face, somebody who you've all seen before here, and this is Wendy Freedman, who is the director at Carnegie Observatories. Wendy works on a wide range of astronomical and cosmological topics. She's probably best known for measuring the expansion rate of the universe. For the first time, there was a big controversy for many years, including in our own building at Carnegie, about the value of the Hubble constant. And Wendy, as part of the Hubble Space Telescope key project in the 90s, helped resolve that for the first time. More recently, she's been working on dark energy and the nature of dark energy. She got the Gruber Prize in 2009. Many of you may know the Gruber Prize is kind of the astronomy equivalent of the Nobel Prize for that work on the size and age of the universe. But one thing that when Wendy became director in 2003, I think, wow, it's been a long time. One of the first things she realized when she became director in 2003 was that if Carnegie was going to remain competitive in the next few decades, that we needed to be involved in the next generation telescopes. This is something that Carnegie we have a very long tradition of, going back to the telescopes at Mount Wilson and now our Magellan telescopes in Chile. That without the next generation, without the new tools, it's just hard to remain on the forefront of astronomy research. And so she's put together a consortium over that 11 years involving countries and various partners, which you'll hear about tonight, for what's known as the Giant Magellan Telescope. And it's a really impressive project, and it's one that really will guarantee that astronomers at Carnegie will remain on the cutting edge for the next few decades. So let's all help me welcome Wendy Freedman to the stage.
Thank you, John, and good evening, everyone. Oh, is there going to be crosstalk here? Okay. I'm delighted to be speaking to you as part of our annual Carnegie Lecture Series and to be here at A Noise Within. I think this is a really nice venue, and I think it's working very well for us. And I'm delighted to be able to tell you about an unfinished and unfolding story in the building of this Giant Magellan Telescope. We're embarking on building what is likely to be one of the most incredible technical feats of the 21st century for a telescope being built on the ground. This telescope will stand 40 meters tall. If you want to compare it with something you know well, it's comparable to the Statue of Liberty, which is 46 meters, but the Statue of Liberty does not bend over and reach the horizon or turn around. It will be housed in a building that is 22 stories high, and more locally, an example, the largest building in Pasadena apparently is the Pasadena City Hall. So if we took 3 meters off the top there, we could enclose the central part of the City Hall. But once again, this enclosure, this 60-meter enclosure, will rotate on a base. And this telescope will have, so the enclosure weighs 2,000 tons. The telescope itself is 1,100 tons. That's over 2 million pounds, the telescope. It's going to have a resolution that's 10 times that of the Hubble Space Telescope, which is our astronomers' current benchmark for resolution. And so that will allow us to see 10 times the detail of the Hubble Space Telescope. And it will have a sensitivity that's about 20 million times the sensitivity of your eyes, or at least my children's eyes, maybe not mine. Changing with time. It will be the first telescope in existence that is capable of detecting life on other Earth-like planets. A discovery that, if it occurs, will surely rank as one of the most exciting of all scientific discoveries. We'll have a system of lasers that will allow it to correct for turbulence in the Earth's atmosphere, and it will allow us to be the first telescope to allow us to look back at the cosmic dawn, literally the first stars and galaxies to form in the universe, and to the first supernovae that will explode and create the chemical elements that are necessary for sustaining life as we know it. So how is it that we are embarking on such an ambitious program? Do we just say, let's build a telescope, let's hire some engineers to design, and then put it together, and then we'll turn our eyes to the heavens? And what motivates us to take on a project of this scale? This is a project that, when it's completed, will have cost about $1 billion, and it will take at least 20 years from its inception to its completion. And this is in an era where government funding is waning for science. And we've been through one of the worst economic downturns since the Great Depression. So can we really seriously contemplate a project of this scale and cost? Now, I just returned home from a meeting of the Board of Trustees of the Carnegie Institution for Science. It took place in Washington, D.C. I just realized I don't have a pointer. Is someone able to get me a pointer? That's the Carnegie Institution headquarters building. It's on P Street in D.C., and it's a building, we're told, that Andrew Carnegie actually wasn't very happy about after it was constructed. It's got these beautiful towers in front. It's a little bit elaborate, and Carnegie was concerned that the institution had spent too much money in creating an administration building. Nonetheless, we inherited this, and it provides us a very nice venue for an annual opening to the public that we have once a year in May. But at the board meeting, each of the trustees of the institution was given an opportunity to speak. And they talked about the new science that this telescope will enable, the discovery potential, and the history of the Carnegie Institution and its leadership role in building the largest telescopes in the world, and both the risks and the excitement of this new and bold venture. And they voted then unanimously to fund the remaining cash pledge for Carnegie's share of the funding for the construction of the telescope, in addition to the very early risk funding that the institution put in at the beginning of the project, that it began investing in 2003. So it's a very historic moment for the institution. A couple of people have recently asked me about progress with the Giant Magellan Telescope and about the funding, about the donors who have helped us, about how we managed to get to where we are despite what appeared initially to be such a low probability of success. And there were people on my own scientific staff who questioned the validity of us going ahead, despite the fact that most of us agreed that it was essential for us to be part of the next generation of telescopes if we were going to keep relevant in this next century. And so I thought maybe I would try a little bit of an experiment this evening. Sorry for you to be the guinea pigs. But rather than just tell you about the technical and the scientific progress, to explain a little more and tell you a story of how the GMT has come about. And so like any experiment, it may not work, but I'm curious to try it. And so I'm going to tell you a little bit about the story to date of the building of the GMT. And I've never actually done this before with an audience. So I'm going to first take a historic detour and tell you why we would contemplate a project of this nature. And the story begins in 1902, and that's when Andrew Carnegie became interested in funding science. And in the Chicago Tribune, the first director of the Carnegie Observatories. So in 1902, George Ellery Hale read in the Chicago Tribune of the gift that Andrew Carnegie was going to make to science. And these two individuals changed, thank you very much, changed the course of astronomical history. So here's Andrew Carnegie standing by, I think, the 60-inch at this time, and George Ellery Hale, also shown here on the right. And Hale came out to Pasadena in 1903. Pasadena at that point was a small little village, really, dirt roads, and went up to Mount Wilson and surveyed the site and found what would turn out to be one of the best astronomical sites in the world. George Ellery Hale was fond of the saying, "Make no little plans." This was a quote from the American architect Daniel Burnham, and it went on to say something to the effect that make no little plans, for they have no magic to stir men's blood. And he meant men in those days. And Hale really took this very seriously. He made no little plans. He started off with a solar telescope at Mount Wilson, which I'm sure many of you have visited, and then the Mount Wilson 60-inch telescope, which Andrew Carnegie helped fund, then went on to build the 100-inch telescope. And for me, that's remarkable because he was already starting to build the 100-inch and plan for it before the 60-inch was even built. And in those days, they used mules to get up the Mount Wilson Trail to take the equipment up to the telescope. It was a phenomenal feat. And the 60-inch telescope was where Harlow Shapley, who was at that time a Carnegie astronomer, made the discovery that our sun is not the center of the universe or the center of the galaxy. And since the time of Copernicus in 1543, Copernicus, you recall, displaced the Earth from the center of the universe. And said that the planets revolved around the sun. And Shapley was able to show that the sun was no longer at the center of the universe, that in fact it's displaced out from the center of what we now know is our Milky Way galaxy and resides in a flattened disk about 2/3 of the way out in that disk from the center of the galaxy. So it was a momentous discovery done at the 60-inch. Hale was convinced that if you built big telescopes with reflecting mirrors, then discoveries would follow. And they did very rapidly. And once the 100-inch was constructed, Edwin Hubble went on to discover that not only are there galaxies in addition to the Milky Way, but that the entire universe is expanding. And Hale was also instrumental in raising the money from Rockefeller to build the 200-inch telescope at Mount Palomar. So successively, he was also involved in the refracting telescope, a 40-inch telescope at Yerkes in Chicago, or actually in Wisconsin, but University of Chicago. And at that time, it was the largest of its kind in existence. So there aren't very many people who have that behind them to have built each of the world's largest telescopes of their kind. So here's Edwin Hubble. This is the astronomer who used the 100-inch telescope. This is Hubble later in 1952 examining a photographic plate. And these photographic plates, the one shown on the right, this is a negative in the sense that the dark things here are stars, which in a positive image would be bright. And Hubble is looking at this glass photographic plate. These were the detectors that astronomers used up until the 1980s, in fact. And he's marked up in the right-hand corner, VAR, exclamation mark, and he's crossed out an N. And what Hubble recognized was he had discovered a kind of variable star. It's called the Cepheid variable star. And it is the essentially best way that astronomers have of measuring distances. And there was a debate in the 1920s at the time that Edwin Hubble was doing this research. And there was a question at that time about whether or not these nebulae, this Andromeda, now we know as a galaxy, Andromeda Nebula, was one of a class of objects. Nebula just means fuzzy in Latin. And the question was, and many of them had very nice spiral shapes, and the question was, were these objects in our own Milky Way, where maybe gas and dust was swirling together, coming together because of gravity, to form new stars in our own galaxy, or perhaps they were island universes or galaxies in their own right. And this discovery of the Cepheid variable enabled Edwin Hubble to determine unambiguously that Andromeda was outside the realm of the Milky Way. In fact, today we know that it's about 2 million light years distant from us. So in astronomical terms, if you remember that light travels at 186,000 miles per second, and at that speed, for example, you would circle the Earth 7 times in 1 second. That's light travels fast in a relative sense. Andromeda is 2 million light years from us. So it's at the distance, and it's a nearby galaxy, by the way. It's one of the nearest galaxies to our own. It's all relative. It would take light 2 million years traveling at 186,000 light years, 186,000 miles per second to reach us. And this is the famous diagram that Edwin Hubble published in 1929. He actually published this. This is velocity increasing up here and distance to the right. What this chart tells us is that the farther away a galaxy is, the faster it's moving away from us. And Hubble apparently didn't notice when he published this that velocity was in kilometers rather than kilometers per second. Even in 1929, they knew that. but somehow got through the editors. This was a momentous discovery. What he learned was that there were galaxies in their own right. These spiral galaxies, one example shown here, is an example of another galaxy outside of our own. And here are some other examples of galaxies here. If we were to get outside of our own Milky Way and look back on our own galaxy face on, we would see these beautiful kinds of spiral arms. Galaxies tend to be close to each other also. They tend to be near to neighbors, also reside in clusters of galaxies. And what Hubble determined was that all of the universe appeared to be expanding. This later was, along with the work of Albert Einstein, his general theory of relativity that he developed in 1915 through 17, allowed both Edwin Hubble and integrated with the general theory of relativity of Albert Einstein to determine that the universe is in fact expanding, that it had a beginning, and it has been expanding from a time, as I'll show you, about 13.7 billion years ago. Now, these are the Cepheid variables that Edwin Hubble first noticed in Andromeda. The Cepheid variables themselves had been known since the 1700s. They'd been cataloged by astronomers. And I'm showing here examples of stars that are varying in brightness. These aren't actually real Cepheids, unfortunately. Would it only be this easy if we could discover them just by looking at them blinking? But it's showing the property of these stars that the fainter ones actually change in their brightness more rapidly than the brighter ones. And it turns out that these stars are actually in motion. Their outer atmospheres are in motion. The stars are pulsating, and they do so in a very regular way, such that the atmosphere is moving in and out. It takes a longer time for bigger stars, longer periods, but it is uniquely related to the brightness of the star. And so if you can observe these Cepheid variables nearby, say in our own galaxy, where you can actually use geometry to determine the distance to the star, then you compare the Cepheids in other galaxies, measure their relative brightnesses, and it turns out to be an extremely accurate way of measuring the distances to galaxies. And so we were able to do this with the Hubble Space Telescope, work that John was alluding to earlier, and now with the Spitzer Space Telescope, which works in the infrared spectrum, we're able to refine these measurements and essentially build up a distance scale of the universe. I always like this cover of Time magazine. When did the universe begin? This was a cover article of 1995. It really is all about time. And we were able to show that the universe was expanding and had been expanding for about 13.7 billion years. And just for reference, the original diagram that I showed you from Edwin Hubble, where he was able to measure the distances to the first galaxies, where he found Cepheids and also bright nearby stars, that corresponds to this tick mark here on this diagram. And we can now make these measurements out to much farther distances. And we were able to resolve the debate over the age and size of the universe. In fact, people used to joke because there were two of us in our building who were making these measurements. We disagreed by a factor of 2 that when they walked around the corner in our building, the universe would stretch, the corridors would stretch. Fortunately, we were able, with the Hubble, to resolve that difference, and we now have the age of the universe to something like 10%. In fact, we're working on proving that value to 3%. We're currently probably at 5%. So a lot of progress since Hubble's time. And of course, you heard about this, I'm sure, last week from a couple weeks ago from Alan Dressler. The Hubble Space Telescope, of course, has revolutionized our view of the universe, named after Edwin Hubble and his contributions to astronomy. So the story of building telescopes continues, and I will, of course, speak about ground-based telescopes. Alan talked about space telescopes earlier. And at Carnegie, the next step really in our evolution was the development of telescopes in Chile at Las Campanas. And in 2000 and 2002, this was culminated in the building of the Magellan telescopes. And many of our astronomers were involved. Steve Scheckman, who just got elected to the National Academy of Sciences last week, just want to note, was the project scientist for the telescope. And this is Matt Johns, who was project engineer. And many of our scientists were involved in building instruments for the telescope. Alan Dressler, who you heard from, Ian Thompson, and Eric Persson, who's in the audience tonight, as is Alan. So this, for the first time for us, was an opportunity to bring together a collaboration, and there were 5 institutions that partnered together to build the Magellan telescopes. Carnegie, together jointly, Harvard and the Smithsonian Institution, University of Arizona, Michigan, and MIT. And this is just showing you the site at Las Campanas. Carnegie owns 100 square miles of this site in the Andes Mountains in Chile, where the telescopes are situated. So how did the GMT start? And that really began, the genesis was with the Magellan Partnership. And as John told you, I became director of the observatories in 2003 and was elected the chair of the board for the Giant Magellan Telescope at that time. And what we called the project at that time was actually the 20-meter telescope, or TMT. Some of you may get the humor in that. The project started, it's another telescope project now. The project started out very small, and we had a board that was comprised of 2 members from each of Carnegie, the University of Arizona, Harvard, separately the Smithsonian Institution, and for a short time we had Michigan and MIT, the partners from Magellan, but the latter 2 eventually had to opt out. And a concept for a 20-meter class telescope had been put forward by Roger Angel of the University of Arizona. And this original concept, his thinking at the time, was it would be a segmented mirror telescope, large segments, each of them would be 8.4 meters in diameter. And in fact, at that time, Angel talked about a twin telescopes, one of which would be on rails that it would actually move, so you could change the baseline and do interferometry with the telescope. We didn't know where the site would be for the telescope at that point, and we didn't know the cost. But the nucleus of the group that had built the telescope, had built the Magellan telescopes, was still very active and eager to begin the work of fleshing out the actual telescope design. And Roger Angel, shown here. This is Steve Scheckman, Matt Johns, Steve Gunnels, who was the project engineer for Magellan. I was chair of the board, and Dan Fabricant at the Smithsonian Institution were involved in the early days. And in those early days, we literally lived hand to mouth. When I began as director, we had, the Carnegie Institution had provided $500,000 for a preliminary concept study. And essentially the idea was, okay, you just finished these big telescopes. I thought they would say no when we first told them about the Giant Magellan Telescope. But they were supportive of us actually looking at the concept and seeing whether it was feasible, understanding that it would take probably decades to build this large telescope, and it was important for our future. So the Smithsonian Institution also got an early donor, and the Carnegie Institution provided additional early risk funding. But there were days at the beginning where Matt Johns and I, so we had, at that point, 2 GMT paid people. That was Matt Johns and an administrative assistant. And then Steve Scheckman and me in our building at Carnegie. And there were days when Matt and I would look at the budget and project out and realize that we didn't have enough money to pay people beyond 2 months. It was tense, and it happened several times. And so we would scale one mountain peak and only to encounter the next. In 2004, an opportunity arose to fabricate the first mirror for the Giant Magellan Telescope. And there were those who actually argued that we would end up very embarrassed if all we ever had to show for the project was a mirror that we couldn't do anything with. But the Magellan mirrors had taken years to fabricate, and when you learn to do something new, it often takes a while to learn how to do it. And so Steve Scheckman and I both felt pretty strongly that it was important to take that risk and to start the mirror and to see whether it could be done. This is the first time one of these large mirrors had been created that was off the central axis. So the Magellan mirrors have one central primary mirror. Light comes to a focus right on the central axis of that mirror. With the GMT, as you saw, there are 6 mirrors in a circle, one in the center, but they all have to act as a common mirror. So the off-axis mirrors had never been done before. And so if we waited to cast the mirror, other telescope groups would take our place, and it might take years before we would have a place in the queue. So the Carnegie board agreed, and with an additional gift from Carnegie, and then Harvard and Smithsonian, Arizona then cast the first mirror in July 2005, and it was to take 7 years to complete that mirror. We didn't anticipate that at that time. So it was a good thing that we started when we did. So in 2003, late 2003, I was chairing a planning committee for a university. It was Texas A&M, the physics department. And an individual by the name of George Mitchell attended the meeting. And George was, turned out to be passionately interested in astronomy. This is the gentleman who invented fracking, so you may know of him even if you don't recognize him. He, it turned out, was very interested in cosmology and astronomy, but grew up at a time when he thought he had to make a living. He had 10 children, and he decided that astronomy wasn't a lucrative profession, and went in to make a little money in the oil business and developed fracking. He was very intrigued by the GMT project and immediately wished to help. And moreover, he was very interested in helping others, inspire others to follow. So he pledged, the first of which was to be a very large gift in the end of $35 million to the GMT. And so in that period, Texas A&M University, the University of Texas at Austin, Australia, and Korea shortly thereafter joined the project. So it became international in scope very early on. And funding for the project continued to grow, and great technical strides continued to be made. We had a conceptual design review in 2006, and then a community review by the National Science Foundation in 2009. Pat McCarthy, who is now the director of the GMT, he's here this evening. He started off as the chair of our science working group for the project, became acting director in 2009 and director in 2010. We brought in Keith Raybould as project manager in 2010, and our newest addition to the project as project scientist is Rebecca Bernstein, who just joined us a few months ago. And the project has grown enormously. The offices that we first had at our Santa Barbara Street building, we had a few of us in the building, grew to 6 or 7, ran out of office space, so we rented space in North Lake Avenue, grew to that eventually, and the project moved to South Lake. There are now over 50 people in the project office, and including all our partners and the work that's being distributed across the world now with our international partners, there are literally several hundred people now involved in the project. So it's been gigantic strides, very fast evolution. So let me turn now to more recent progress. So here's the site. There are auxiliary buildings being built down from the summit, so we're keeping the telescope as clear from everything as we can. You can see, again, the enclosure here, which is open to the outside air, which allows air to blow through the enclosure to keep the temperature as close to ambient temperature as we can. And that ensures that the mirrors don't get out of equilibrium in temperature. It doesn't cause unnecessary turbulence on the surface of the mirror. You can see this opens up here, and then in the front here, you'll see in a moment, this will rise up, and so that you can protect the telescope from the elements. It does snow at Las Campanas, it certainly rains, although 300 nights a year are clear at this site. It's a superb site. The site has been leveled here. You can see it's flattened. I'll show you the blasting in a moment. There's actually room for 2 telescopes on the site. So Roger Angel may get his wish, or some other group may eventually decide to build another telescope on the site. But what we did know is that once we had blasted, we wouldn't want to do that again once the telescope was on the mountain. So here are our current partners, Arizona, Chicago, Astronomy Australia Limited, the University of Texas at Austin, Texas A&M University, the Korea Astronomy and Space Science Institute, the Harvard-Smithsonian Center for Astrophysics, Carnegie Institution for Science, and the Australian National University. So we now have a very large board, 17 members, and we meet several times a year by phone and also in person, and we rotate amongst the different partners. You can imagine there are times when we have things to do that are differing interests of different partners, different countries, different institutions. But what I will say is we've managed to function as a board in a very collegial way, and the partnership has been a real pleasure, in fact, to build this telescope, even with all the complexity. We are using this novel mirror technology that was developed by Roger Angel at the University of Arizona. And so here you can see the 6 mirrors again on the outside, each one of which is 8.4 meters in diameter. And this central one, which has a hole in it, so it has the smallest area of all of the mirrors. And there is, for each primary mirror, a secondary mirror, and the secondary mirrors are 1 meter in diameter. So the primaries are 8.4 meters, the secondaries are 1 meter. And the secondaries are adaptive in the sense that they will be moved much more quickly to allow us to compensate for turbulence in the Earth's atmosphere. And so the primary mirrors will be corrected every 30 seconds or so. The figure of those mirrors will be corrected. That's what we do for the Magellan telescopes now. But the ability to correct these mirrors on a few hundredths or even thousandths of a second, the adaptive mirrors, allows us to take advantage of this resolution, the very long baseline of the whole telescope, which determines the overall resolution. So this adaptive optics, we're all familiar with. If you look down a road that is heated in the summertime, you can see this blurring. You actually see the effect. And the idea is that as light comes from a distant object, it might get distorted. The waves here are distorted. And the idea, and I'll show you in a moment, is to correct the wavefront and actually get back to the original image. So you see the before and after correction. And this is an example, the Large Binocular Telescope built by the University of Arizona and several other partners. You can see here, this is showing an image initially. Let me get that back again. Without adaptive optics turned on, and watch as the system turns on, you can see it resolve into 2 stars here and a 3rd star here, which is impossible to see in the original image. So if we're just observing from a telescope from the ground, ordinary, what astronomers refer to as astronomical seeing, you would not know that there's all this detail here. And this is now functioning. This was one of the biggest technical risks to the project when we started, was understanding how to do this adaptive optics. And now that's been demonstrated both at the Large Binocular Telescope and also at our own Magellan telescopes. So I mentioned earlier, the GMT is going to have 10 times the resolution of the Hubble Space Telescope, and it also has 100 times the light collecting power of Hubble. It's an enormous gain in resolution. In terms of sensitivity, and just to get a sense of the resolution, what that means, if you take a dime out of your pocket, look at the writing, look at the picture on the dime. It's pretty small. It's pretty hard to read, even if you have better eyesight than I do. And if you were to go to Las Vegas holding that dime, and we in this audience were using the GMT, we could turn the GMT to your dime, and we could resolve what's on the face of that dime. It's pretty spectacular. And if you went to the moon, lit a candle, we could also see that. Very sensitive. So these are some simulations that were done by someone in the project office, Chen Peng. This is, again, what astronomers refer to as reasonably good seeing, 0.6 arc seconds, which is how much light is concentrated in a particular area. And this is what you can get on the ground without making corrections. In fact, my husband is at Las Campanas right now. He's observing with Magellan. I spoke to him last evening, and the seeing was 0.6 arc seconds. Pretty good. Nick Moss is a camera, infrared camera, was working on the Hubble Space Telescope for a period. And you can see that the resolution increases. This is, again, so Hubble's a 2.5-meter telescope in space. NIRCam will be an infrared camera that will be on the James Webb Space Telescope. So that is a 6.5-meter telescope. You can see again how the resolution improves. And now we'll go to the GMT, and you can see the spectacular improvement in resolution. So if you go back to that original image and what we get on the ground right now with Magellan, what we're going to have with GMT. So every problem that you can think of studying in astronomy, this is why astronomers are really excited about having GMT in a few years. It's like putting on eyeglasses again. The clarity with which you can see individual images is a huge gain. So what is the science that we will do with GMT? And there's an enormous amount of science that is coming our way. In 1995, we didn't know of any other planets in the universe other than those in our own solar system. And at that time, we thought we had 9 planets, but Pluto hadn't been demoted yet, voted off the island. Now we know we have 8 planets, but those were the only planets that were known at that time. And then a discovery was made that there are planets that are orbiting other stars, and that just has continued to increase. We've learned of all sorts of different kinds of worlds. In fact, the natural assumption at that time was that when we found other planets, they would resemble those in our solar system. So we know that, for example, the terrestrial planets, the Mercury, Venus, Earth, Mars, the smaller planets, rocky planets, are closer into the sun than the outer planets, Saturn, Jupiter, Neptune, and Uranus, the larger gaseous planets. And the idea went, well, you couldn't have a gaseous planet that's massive near to its parent star because it would have destroyed the atmosphere. And the way that planets would have to form is what we saw in our own solar system. All the planets in our solar system are in a disk. They're a narrow disk, and we assumed we'd see the same. But when the first other planets were discovered, immediately almost, there were these massive Jupiters, hot Jupiters we call them now. They're close into the central star, right where all the theorists told us we could never have them. There are many of these hot Jupiters. And the inclinations of these planets turned out to be all over the map. They're not just lying in an inclined disk. And in fact, our solar system turns out to be unusual in the end. There are many ways that astronomers have of finding these planets. One of the ways is to look actually for the transit, the motion of a planet in front of and then behind the star. And you can see, so as in this example here's the planet going around its star. And if you look, you can see, so as it comes in front, you block the star, you see this big dip. Then as it goes behind, you block the light of the planet, there's a little dip. And comes around again, going to come in front of the planet, in front of the star, you get a big dip in light as you block the light from that star. So astronomers have become very adept at measuring, very sensitive now measurements of these transiting planets. And there's a satellite called Kepler that you may have heard of, been in the news recently. There are now over 3,500 known and candidate exoplanets in multi-planet systems. This is just staring at one region of the sky and observing the stars and the changes in their brightness over time. And you can see these exoplanets here. These are individual planets going about the central stars, moving slowly here, and then these objects here that are close in to their central stars. But the discovery space that has opened up is enormous. We don't yet know. So there are many planets that have been discovered that are like Jupiter, like Uranus, like the more heavy objects that we know about. And we're just getting to the point where the technical limits are being such that we can actually find things that are a few times the mass of the Earth. We will find soon Earth-mass planets, but we will, in fact, there are candidates. It will require the GMT to actually get spectra of them, to actually measure orbits of those planets and determine the actual masses, rather than just the radius, which you can get from observing the transits. So those are discoveries that will, I think, be enormously exciting, and GMT is poised to do them. Hello? We'll also be able to look back in time with the GMT. The finite speed of light it means that essentially in astronomy we have a built-in time machine, so that the farther back we look in distance, the earlier we are seeing the light that left those objects. So we will look back to this cosmic dawn at the current time when we look with the Hubble Space Telescope. The faintest smudges, the most distant objects, we don't have much information on. With 10 times the sensitivity of Hubble, we will start to actually witness directly the assembly of galaxies at the earliest times when they formed. We've only learned in recent decades that, in fact, most of the matter in the universe is very different than the matter that we're made of, ordinary what we call baryons, but the chemical elements that are familiar to us, carbon, nitrogen, oxygen, all the elements that we need, for example, for life. It turns out that most of the matter in the universe actually doesn't emit any light. It is dark, and it only is interacting gravitationally, which is the way we know of its existence. And starting out in the 1930s, there was an astronomer at Caltech by the name of Fritz Zwicky who noticed that the velocities that he measured for galaxies now in clusters, motions of those galaxies, were much faster than they would have been if there wasn't more mass there than you could see. That is, the galaxies would have left the cluster, flown off long ago, unless there was more matter there that was holding them on, binding them to the cluster. But that was actually ignored for decades because there was no explanation. People didn't understand what the source of it was. The astronomer at Carnegie, in fact, by the name of Vera Rubin, noticed the same effect in stars, the motions of stars within galaxies. They also were moving faster than they should have been if there wasn't more mass there that was holding them bound to the galaxy. In the 1980s, when it became possible to measure X-rays by going above the Earth's atmosphere, again, it was discovered that there was gas out there in, for example, clusters of galaxies that was so hot, hundreds of millions of degrees, that again, it would have evaporated if there wasn't something else there, more mass holding it bound to the cluster. And then similarly, Albert Einstein predicted, again, his general theory of relativity showed that matter curves space, and the curved space shows matter how to move. And he predicted that there would actually be a lensing of light as it came through. So if you look at a distant source coming through a massive cluster of galaxies, that the distant sources, the light would be bent by the presence of the cluster. And you see these arcs here in this image that are precisely a result of this gravitational lensing. All of which is to say there's an enormous amount of evidence that has been built up over the last many decades that indicate that there is much more matter in the universe than we can see. But we still don't know what it is. There are other examples of some beautiful astronomical lenses. So what could the dark matter be? There are a lot of ideas early on that it maybe could be rocks, planets, remnants of old stars, cold gas, you read the list, black holes, dust, and so on. But there were many searches in the 1980s and 90s looking for astronomical remnants that might be the source of this dark matter, and none of these proved to fit the bill. The best idea as yet is that there's some undetected particle that was formed at the time of the Big Bang. And this dark matter, this is a simulation now showing flying by, so that on the right is shown the dark matter. The ratio of the dark matter to the luminous matter is about 6 to 1. There's more dark matter in the universe than luminous matter. And the dark matter and the galaxies are part of this, what astronomers now refer to as a cosmic web, this structure that has grown in the universe. So these are some of the things that we will do with GMT, is to understand the nature of dark matter and galaxies. I will. Another discovery I just want to touch on is discovery of the acceleration of the universe. This is something that happened in the late 1990s by a couple of different groups working and studying explosions of stars, supernovae, at the end of their lifetimes. So these are stars, a particular kind of supernova that is in a binary system, double star system, one of which is a very evolved star. And its companion star is losing matter to this evolved, very dense system as it evolves. And eventually, so much matter goes onto the white dwarf here that it exceeds a certain mass limit and explodes. And the explosion is so bright that it actually can be seen over most of the visible universe. And so there are signposts to allow us to chart the expansion. And the surprising result was that the universe is not just expanding, as Edwin Hubble had discovered, but it's actually accelerating in its expansion. And that was an enormous surprise, although it had been allowed by Einstein's general theory of relativity. A Nobel Prize was awarded a couple years ago for that discovery in physics, but we still have no understanding of what is causing the universe to accelerate, and whether or not this dark energy changes over time or is constant over time. That's something, again, that GMT will help us to discover and understand. This has been referred to as the biggest mystery in science, and also the case that particle physics, if you actually compute what you expect to be the contribution to this dark energy or the vacuum of space, you would calculate that it is much larger than what we observe. What do I mean by much larger? It's not like a factor of 2 or a factor of 10. It's 120 orders of magnitude larger than what we observe. And there are ways to try and understand, not do the calculation where we don't yet understand the physics very well, where it hasn't been tested in laboratories. That's a big help, because then it's only 60 orders of magnitude. So there really is something that we don't understand, and that telescopes of the future are going to be needed to help us understand. And just to summarize, we don't yet know the nature now of 95% of the universe. Most of the composition of the energy and mass is in this unknown dark form, both dark energy and dark matter. So, a little more on the technical progress of GMT. The mirrors are being fabricated in the Mirror Laboratory. It's underneath the football stadium at the University of Arizona. That's an obvious place for a mirror laboratory, don't you think? And Roger Angel was looking for some space when he first started making these mirrors. It's a very unusual technology. These mirrors are made in a rotating oven, a furnace that is spinning at 5 revolutions per minute. Doesn't sound like a lot, but when you see it in this room, which is effectively the size of this auditorium, spinning 5 times a minute, this thing really does move. You put in glass chunks and you melt it, heat it to about 2,000 degrees, and then the glass is allowed to cool very slowly over a period of months so that it doesn't develop a lot of cracks or bubbles. Here you can see it rotating over here as the glass is melting. And this is, it was a huge challenge to do these first mirrors. The surface of the mirrors now is 19 nanometers, 19 billionths of a meter is the fluctuations in the surface of these mirrors. So just for scale, recall a hydrogen atom is about 0.1 nanometers. So we're getting down into something like 100 thousandths of the width of a human hair. It's really spectacular contribution. And this is over something that's 8.4 meters in diameter, 27 feet in diameter. And another way to think of that is if you took one of these mirrors and you spread it out coast to coast from Los Angeles to New York, and you looked at the surface of the mirror, polished to this smoothness, the height of the tallest mountain, if you could polish it down to that level of accuracy, would be about an inch. It's from coast to coast. So it's really a spectacular technical feat, never been done before. The first mirror is now accepted. It's been coated. No one else can touch it. The tendency was to try and keep polishing, make it even better. But of course, if you made a mistake, you'd have to do the whole thing over. So we stopped them from doing that. The second mirror was cast a few years ago. This is it coming with the oven being opened. The rear part of that second mirror has now just been completed. The third mirror was cast in August of this year, and the glass has arrived at the mirror lab for the fourth mirror, and the GMT board has approved going ahead with a contract for the fifth mirror. So we are in pipeline production for the mirrors. This is one of the thin shells, one of the secondary mirrors, the adaptive secondary mirrors. These are controlled by magnets that help to change the shape of the mirror very quickly to compensate for the turbulence in the Earth's atmosphere, and that's been demonstrated. Another technical, the biggest technical risk to the project when we started was determining whether or not these large mirrors could be made. And in fact, there were several points where we actually wondered whether this was going to succeed. It has. The next is to be able to use the mirrors as a single primary, all the segments focusing the light in the same place. And that requires extraordinary precision. There was a group that developed a camera, which they've tested at the Magellan telescopes, that allows them to measure essentially the distance between the primary and secondary mirror at 1 part in 500 million. It's a huge technical success again, and that's been demonstrated, and they've shown that it can work for the different mirrors. This is a single mirror for Magellan where it was tested, but they actually put a delay into that so they could test what will actually happen with the GMT. So the site, as you saw, has been leveled. This is just preparing the site for the leveling, and we blasted the site starting in March of 2012. This is the actual blast, and you can see there's red, white, and blue here. And the reason for that is it turns out that the colors of the flags of Korea, Australia, Chile, and the US are all red, white, and blue. So at least now, while we only have 4 countries involved, it's perfect. But we hope to break that soon by having some additional countries join us. So the mountain now has been leveled. Here's the site as it looked just before all of it had been leveled. And here's a comparison before and after. So if you just look as it was. Simple. So there were 9 meters at the highest point that had to be taken off the mountain. That in itself was an interesting process. I don't have time to go through that right now, but there are a lot of mining companies in Chile that are very experienced at explosions. So we made use of that. Here are some of the recent design studies for the mount and the enclosure, and worried about how the telescope will move, for example, if there's wind or maybe an earthquake or something of that nature. This is highly exaggerated, I assure you. But it is important to understand how the telescope will move in various conditions. And here is the enclosure, a design for the enclosure. It's not the real one yet, unfortunately, but that will be soon enough. And here is where we are in the timeline. In 2014, the site blasting has been done, and we wish to begin the telescope construction this year, and we're working very hard to put the steps into place to make that happen. And then the idea is we will commission the telescope with 4 of the mirrors, not all 7 initially, and begin taking first light and probably early science data in 2021. And the idea is at that time to have 4 mirrors and 2 instruments working, one of which will be important for studying exoplanets and the other, the early light from galaxies in the universe. So where are we at this point? A huge amount of progress, successful completion of the first off-axis mirror, the casting of the second and the third, purchasing the glass for the 4th. We've approved the 5th. As you've seen, we've leveled the site. The instrument concepts have been reviewed. We have a roadmap, not just for the 2 instruments at first light, but out into the decade ahead. A prototype for the adaptive secondary has been commissioned at both the LBT and also at Magellan. We had a series of reviews over a period of 12 months where we looked at the telescope, we looked at the adaptive optics system, we looked at the enclosure and facilities. We had outside people, experts come in to review those. That culminated with a design review of the entire system and then a cost review. And essentially the recommendations of those committees, the last 2 committees, were ready to go. The design is sufficiently complete to begin construction, and we should do that. We have 9 partners that have signed our legal, what we call our founders agreement. We're under discussion with 3 additional potential partners, and we are poised to start construction in the next few months, which we are hoping to do. So let me just leave you with some final thoughts. Our universe has turned out to be quite extraordinary. It is vast, it is expanding, it is filled with exotic objects and new kinds of matter and energy, and I think it's very unlikely to be through surprising us. And so as we enter this decade, as we build the Giant Magellan Telescope, I hope you'll come back and hear about the exciting science that we find. Thank you.
questions? Several. We're going to start here. Go ahead.
This design for this telescope, as opposed to the techies and the Europeans, why was the choice made for this particular one? I know the others were similar.
Yeah, so the question is, there are two other groups that are building large telescopes, planning on building large telescopes in the next decade. And those two have different technologies, and they are both similar in the sense that they have small primary mirrors, about 1 meter in diameter. So one of them has about 500, and the other 1,000, I guess. And ours are these big segments. And so really it was the heritage of each of the groups. We had built the Magellan Telescope. We knew how to work with these big, large mirrors. And the other groups had worked with smaller mirrors. All of them turn out to work. So in the 1980s, when people were thinking about the next generation after Palomar, nobody knew how to build bigger telescopes at that point. So the Palomar 5 meter is a large, solid chunk of glass. And if you built something that was bigger than that, it would have sagged under its own gravity. So something had to change to allow you to build something bigger. And so different groups tried different things. So the Roger Angel mirrors, I didn't mention that not only are they so spun in an oven, there's actually a mold within the oven that allows you to put in silicate cores. There are in fact about 1,600 of them for each one of the 8.4 meters. And you put the glass in, allow it to slump and melt around the mold. Then you can take the mold out later with high pressure water. And what you're left with is a honeycomb shape. And the mirror is only about 20% of the weight it would have if it was a solid chunk of glass. And not only that, if you had to polish something like the Palomar telescope, solid chunk of glass, these new telescopes are much faster. They're much more curved. And so you would have had to take out so much glass that calculations were it would take about 50 years to do that. So we didn't want to do that. So this is what we did. And last time we didn't know. So the Keck telescopes in Hawaii are made out of 1 meter segments. There are 18 of them for the 10 meter telescope. And they have to be combined. And the Magellan telescopes are these rigid one piece. And at the beginning, and then there's the Gemini telescope, which is actually a thin mirror. Nobody knew what would work. They all did. And so I think all of the technologies that we're talking about now for this next generation are likely to work, and there's probably no reason to prefer one over the other. But I will say this one is uniquely suited for studies of exoplanets and eventually imaging because of the superior quality of the mirrors. And we don't have to combine the light from hundreds of mirrors where you have lots of edge effects. So it has that advantage. Each has their own advantages and disadvantages.
There's a question back there.
Oh, yes. Tell us more about the secondary mirrors used for the adaptive optic system. I know they're only going to move, a micron or so, but that's a big piece of glass or material. It's going to be moving quite rapidly.
Yeah, so these are very thin shells of glass. They're very, you have to be very careful with them. They've been demonstrated now, as I said, at the LBT and Magellan, but early on, some of them did break. So we think we know now how to deal with them. But there are these magnetic coils. They're not unlike the coils that you have, in your stereo system. And these will be controlled at hundredth to thousandths of a second timescales. And so the laser system, these are sodium lasers that will be used to shine up. There's a layer in the Earth's atmosphere, a sodium layer, about 90 kilometers up, and bounce back down, and so that you can apply these corrections over a fairly narrow field of view, but still quite interesting, especially for things like exoplanets and interiors of galaxies and but not, so it's complementary, I would say, to space. You're going to have much better imaging over wide fields in space, but you have very high resolution in narrow fields, say a couple of arc minutes.
Right up front.
How are you setting up the priority list of the researchers who get to use this once it's ready to go?
The short answer is those who pay for it. So it's an expensive proposition, and part of the reason that, that institutions are willing to sign up is to let their astronomers have access to this facility. So there won't be very many people early on who would have access to that. Our hope is eventually that the astronomical community, the broad astronomical community, will have access, but that will require that there be National Science Foundation funding, and right now they've said they don't have funding for any of these facilities in the next decade. And then scientific priority. So once you talk about which institutions would have access and which astronomers, then there'll be a time allocation committee that astronomers will write proposals, and then a time allocation committee will decide the priority after that. In the back. It's okay.
What sort of image artifacts do you expect from the unusual 7-mirror?
So partly, a lot of this time, this telescope's going to be used for spectroscopy, and so you really don't need to worry about that. I mean, you're collecting light, putting it through a slit, dispersing it into a spectrum. But we will see with time how the imaging goes. The Magellan telescopes are the best imaging telescopes on the ground without any correction for the Earth's atmosphere. There are no other telescopes that function as well as it does in seeing limited conditions. So we'll have to see how the telescope operates. But as I said, in terms of most of the work on the telescope is going to be for spectroscopy. In the back.
What type of glass are you using for your mirrors, and what material are you using to coat the mirrors as well? Are you using ULE glass or?
So it's borosilicate glass, and it's interesting glass. It's actually manufactured in Japan. And what we were told originally, and I'm not even sure about the accuracy of this anymore, but is that sand came from a beach in Florida and then shipped to Japan. The true part of the story is that there is a company in Japan that uses these clay pots to manufacture the glass. It has a huge, the glass is very pure. And it's not zero expansion glass, but it's low expansion glass. And then it's shipped back comes to the University of Arizona, and they actually inspect these chunks of glass and take out ones with impurities. And then, so after it's melted, tested, cast, shipped down to Las Campanas, and that would, at least for the Magellan mirrors, what we did was ship them, or take them by truck in the middle of the night with a police escort from Tucson to Long Beach, and then put them on a ship and take them down to Coquimbo in Chile. And then again, police escort in the middle of the night up the mountain where we had to widen the road in several places. And I'm getting to the coating part. And then there's a coating facility, as there will be for GMT also, and it will be a thin coat of aluminum. And so there's a chamber, a vacuum chamber, where the coating for the mirrors will be placed on. They'll be taken out of the telescope about every 2 years. So you'll rotate amongst the 6. So every 3 months, you'll be taking out one mirror and then putting in, there's a spare. We'll do 8 mirrors in total. And so take one out, illuminize it, so you don't have to have a lot of downtime when you're doing that. And they'll be coated. So there may be future coatings that we'll use by the time it's developed, but the plan now is for aluminum. Yeah.
If the universe started expanding 37.5 billion years ago,
13.
13. What was going on before that, and was it just?
So it's a good question, and people ask it a lot. Scientists also. It's a little bit, though, like asking what's north of the North Pole. It's a hard question to answer. So the simple answer is we don't know. We really don't know. But there's been real progress in the last several decades in understanding. So one of the things that Einstein tried to do before the end of his life was to unify the different forces in nature. And we have a real problem with gravity, which we know operates on the largest scales, is really important over astronomical distances. And then quantum mechanics, that is the world of the very small. And in the early universe, you have both. You're going to have very strong gravity because the universe is very dense at that time. It's also very small. So quantum mechanical effects are going to be important. And there's a theory called string theory, which is, at the present time, the best appears to be the best way of trying to bring those, understand how those two forces would be unified. It's helping astronomers and physicists understand more of what the early universe would be, but there's no predictive power for what causes, for example, there appears to have been a very early period of expansion. Astronomers refer to it as inflation, an inflationary epoch where early in the universe you had noise from quantum fluctuations, the differences in density that were stretched to very large sizes as the universe expanded and accelerated very rapidly early in the universe. But string theory can't predict that, or at least it could, but might have to predict 500 million other universes where different things happened. And so there have been some very interesting recent results. So if there was this inflationary period, what we do see, what there is evidence for, is this early expansion. You see in the microwave background now the remnant radiation from the Big Bang. It's about 3 degrees above absolute zero. The remnants of these quantum fluctuations, differences in density, which were the seeds that grew to be the structure that we see today in galaxies and clusters of galaxies in this cosmic web that I showed you. So recent results actually are getting back to an epoch where there would have been gravitational waves, an imprint from gravitational waves from the Big Bang explosion that we see on this surface about 380,000 years after the Big Bang. So we're getting closer and closer to the Big Bang and understanding the earliest moments, but I still don't, nobody has an answer to your question of what came before the Big Bang. But a huge amount of progress and physical understanding of what actually happened in the earliest moments. It's really quite spectacular.
Can we take one more question?
Yeah. Dark matter is described as matter that's dark, but what leads us to believe that in fact matter is causing is the gravitational effects are caused by matter? Because I mean, as you explained before, our perspective has shifted as we change with the invention of the telescope. We were able to look and see that the Earth wasn't the center of the universe, then the sun wasn't. Why, just because matter seems to be a seen thing around us, why would we automatically assume that that's causing the force of gravity? It's kind of a strange assumption, right? Based on logic.
Ultimate Copernican principle. So the more we learn, so we think we're at the center of the Earth is the center of the universe, sun is the center of the universe. Now we're not even made out of the stuff that most of the matter in the universe is made out of. But so what we do see in terms of dark matter is that the behavior, so the motions of stars within galaxies or the motions of stars in clusters of galaxies are very similar. So what we're seeing is consistent with it being matter. Some kind of matter that's interacting gravitationally the way luminous matter does. It's clustering in clusters of stars. It's clustering within galaxies. And so it appears to be a particle, some remnant from the Big Bang. The best candidate, something people call a weakly interacting massive particle. If it's real, then it looks very likely that it ought to be detected in the next decade or so. So there are a lot of experiments, very different experiments. Some of them are being done in underground mines, so taking detectors that have silicon and germanium, looking for a WIMP to come by and cause a sound wave essentially so that you can actually detect the signal for that if it's real. These things, if they're real, are coming through this auditorium right now. They're moving at a few hundred kilometers per second, and they're coming through us because they interact so weakly, we have no way of knowing that they're there.
I just think it's a strange assumption that now you're saying that most of the matter in the universe, or this effect, is dark matter causing this, yet you can't see it. So we're assuming that the matter that we see and call matter is causing the majority of the effect. Why make that assumption? That's a question I'm asking.
So the majority is actually dark energy, which is very different than dark matter. And we're not assuming they're hypotheses that we're going to test.
Okay, thank you.
They could be wrong.
No,
they could be wrong.
I agree, not you, but a lot of the talk, and I'm just like, this doesn't really make sense. just to my basic logic. I don't. But again, it's sort of the way that we've looked at things based on our past paradigm. So that's why I say I use the first example that is our paradigm, right? Our perspective expands, that the paradigm needs to shift.
It has. It's pretty exotic compared to
what
what we know we're made out of. But as I said, we'll determine whether this actually empirically can be tested.
I'm sure if there are any other questions, Wendy would be happy to answer. Just come on up and let's thank her again.